Hello everyone, this is lecture 14 in real analysis and we are going to talk about sets. So we already talked about sets in previous lectures. We used sets and it was assumed that you have some prior knowledge about sets. However, in this lecture we will talk in more detail. We will provide some relevant definitions. In particular, we are going to define the union and the intersection of sets and discuss their properties. And we will also define the complement of a set and discuss its properties. Please like, subscribe, and comment on this video to support this work. So let us recall that a set is a collection of objects. So we can describe sets by listing objects in them. For example, we can have a set with elements A, B, and C. Or we can describe sets by using set builder notation by stating the properties that all of the elements of the set should satisfy. So for example, here is a set of all real numbers that are in between 0 and 1. So this is the open interval 0, 1. So this is all x in R, and this column here, it means such that x is greater than 0 and less than 1. So every element of the set A should be between 0 and 1, and it should be a real number. So if an object x is in the set A, we say that x is an element of A, and we write x in A. If x does not belong to A, we write x does not belong to A. So this is how we can illustrate this. So suppose A is everything that is inside this region. So if we have a point x inside this region, then x belongs to A, and if the point y is outside of this region, that y does not belong to A. So this is called a Venn diagram, and Venn diagrams are really helpful in trying to understand properties of sets. So the next definition that we want to discuss describes the following situation. So suppose we have a set A such that it's inside set B. So every element of A is also an element of B. In this case, we say that A is a subset of B. We may also say that B contains A, and we write A is a subset of B. So if A is a subset of B and A is not equal to B, then A is a proper subset of B, and we denote this by writing A proper subset of B. And two sets A and B are equal, and we write A equals B if every object of A is in B and every object of B is in A. So basically, if A and B consist of exactly the same objects, then these two sets are equal. So in analysis, in some proofs, it is used that two sets A and B are equal if and only if A is a subset of B and B is a subset of A. So the proof of this theorem is very straightforward. It follows directly from the definition of the equality of two sets and the definition of the subsets, so we are not going to provide it here. So let us recall how we denote intervals. So let A and B be real numbers such that A is less than B. Then the closed interval AB, when we have brackets around A and B, is the set of all real numbers x such that x is greater than or equal to A, less than or equal to B. So basically x could be equal to A and could be equal to B. So the bracket denotes the fact that x could equal to the boundary that is next to the bracket. The open interval AB is defined to be the set of all real numbers x such that x is strictly between A and B. And then we have these two sets where there is one bracket and one parenthesis. So where the bracket stands, we have a not strict inequality, and where there is a parenthesis, there is a strict inequality. So this symbol here denotes the empty set. Empty sets contains no elements, and often by U we denote the universal set. So the universal set is usually clear from the context. So if we are talking about sets of real numbers, then the set of real numbers will be the universal set. So for example, in these definitions, the universal set U is equal to R. If we were talking about complex numbers, for example, then the set of complex numbers would be the universal set. So universal set is usually clear from the context. So let us define the intersection and the union of two sets. So let A and B be sets. Their intersection is defined as follows. So A intersected with B is the set of all objects X such that these objects are both in A and in B. So on a Venn diagram, the intersection would be here. These would be all of the elements that A and B have in common. The union of A and B is the set of all X such that X is in A or X is in B. So on the Venn diagram, the union of A and B would be the set of all elements such that they are either in A or in B. So it will be this region, this shaded region here. So let us consider an example. Let set A be the set of elements A, B, C. Here we have a set B that consists of the elements 1, 2, 4, A and B, and the set C consists of the numbers 1, 2, 3. So let us write down what is A union B. This is going to be A, B, C, 1, 2, 4, and we are not going to write A and B because we already wrote them down. So the A union B is the set of elements A, B, C, 1, 2, 4. A intersection B is the elements that A and B have in common. So those would be elements A, B. And let us notice that if we look at A intersection C, the set A and the set C, they have nothing in common. So A intersection C is an empty set. In this case, we say that the sets A and C are disjoint. So let us discuss some properties of the operations on sets. So let A, B, and C be sets. Then A union B is the same as B union A. A intersection B is the same as B intersection A. If we take A union B and then compute union with C, this is the same as to take union B union C and that then compute union with A. And similarly for the intersection. So we have here equals A intersected and B intersection C is in parentheses. So this property over here is, I usually remember this like this, A times B plus C. So instead of intersection, you write times, and instead of a union, you write plus. And so by the distributivity of real numbers, you have AB plus AC. So this has nothing to do with the proof. It's just how to remember this property. So we are going to have that this is A intersected with B union A intersected with C. And the next property is basically we take property 5 and replace intersection with union and union with intersection. So this is A union B intersected with A union C. All right, so these are some properties of sets. So these first four properties, the proof for them is really straightforward. It comes from the definition. We are going to prove property 5. So in order to prove property 5, we are going to use the theorem that we stated just a few minutes ago. So two sets X and Y are equal, so X is equal to Y, if and only if X is a subset of Y and Y is a subset of X. So if this is our set X and if this is our set Y, then we are going to show two inclusions. The first inclusion is that the left-hand side of equality 5 is a subset or equal to the right-hand side of equality 5. And the second inclusion that we are going to show is that the right-hand side of the equality 5 is a subset or equal to the left-hand side of equality 5. So let us go ahead and prove inclusion 1. So in general, let us think about what does it mean that a set X is a subset of a bigger set Y. It means that if we take any point little x in the set capital X, that point also is going to be in Y. So for every x in capital X, x is in Y. This is true if and only if x is a subset of Y. So in order to prove that this set over here is a subset of this set that I am boxing right now, let us suppose that X belongs to the set on the left-hand side, so A intersection with B union C in parentheses. What we want to show is that X belongs to the right-hand side of inclusion 1. So we want to show that X belongs to A intersection B in parentheses union A intersection C. So since X is in the intersection of A and B union C, it means that X is both in A and in B union C. Remember, intersection is what is in both sets, right? So we have that X is in A and X is in B union C. So now let us try to understand what does it mean that X is in B union C. So if we have two sets B and C here on the Venn diagram, it means that X is a subset of the union. So X could be in B, X could be in C. X in B union C implies that X is in B or X is in C. So let us consider two cases. Case 1 is when X is in B, and case 2 is when X is in C. So in case 1, we have X is in B, but we also have that X is in A. So if X is in both B and A, then X is in the intersection of A and B. So let us stop for a moment and try to understand what we have. So we have that X is in A intersection B, and what we want to have is that X is in A intersection B union A intersection C. So let us try to think for a moment. If we have two sets X and Y, and if little x is in the set capital X, then it's also in the union of X and Y. So X is in capital X implies that X is in capital X union Y. So similarly, if X is in A intersected with B, it means that X is in A intersected B union A intersected C. So X only has to be in one of these sets to be in the union, and it is in A intersected B. Okay, so this is how we prove that X is in the set in which we want it to be in case 1. Now let us look at case 2. So we have that X is in C, but we know that X is also in A. So X is in A intersected with C. But by the same reasoning, if X is in A intersected with C, then X is in A intersected with B union A intersected with C. Because in order to be in this union, X just needs to be in one of these two sets, and it is in this set right here, A intersected with C. So X is in the set in which we want it to be. So that finishes the proof of inclusion 1. So let us now prove the reverse inclusion, inclusion 2. Let us suppose that X is in this set over here, in the set A intersected with B, union A intersected with C. We want to show that X is in the set A intersected with B union C in parentheses. So again, as before, let us try to understand what it means that X is in this set over here. So X is in the union of A intersected with B and A intersected with C. So that means that X is in the first set or in the second set. So we have that X is in A intersected B or X is in A intersected C. So we have two cases now. Case 1 is when X is in A intersected B, and case 2 is when X is in A intersected C. So let us look at case 1. So X belongs to A intersected B implies that X is in both sets. So X is in A and X is in B. But just like we reasoned before, we can say that X is in B implies that X is in B union C. So we can say that the whole statement here implies that X is in A and X is in B union C. But then X is in the intersection of these two sets, A and B union C, and this is exactly where we want X to be. We want it to be in this intersection. So implies X is in the intersection A and B union C. So now let us look at case 2. Let us suppose that X is in the intersection A intersected with C. So that means that X is in both A and C, so X is in A and X is in C. But X in C implies that X is in union of B and C. So overall, we have that this statement here implies that X is in A and X is in B union C. But then X must be in the intersection of A and B union C, just like we want it to be. So then X is in the intersection of A and B union C, just like we want it to be. And so in both cases, X is in the intersection A intersected with B union C, and this is exactly what we wanted to show. So this finishes the proof of inclusion 2, and it finishes the proof of equality 5, so QED. So we are going to finish this video by the definition of complement of a set. So let A and B be sets in the universal set U. So we can illustrate this by the following diagram. So we have two sets A and B in the universal set U. So the complement of A relative to B is the following set. We usually say B minus A is equal to all X, such that X is in B, but X is not in A. So on the Venn diagram, it would be this shaded set. All right, and in general, if we say A complement, then we mean that this is the complement of A in the universal set U, so this is U minus A. So this is the set of all X such that X is in U and X is not in A. And on the Venn diagram, A complement looks as follows, is this shaded set. So, for example, if the set A is the set of integers 1, 2, 3, and if the set B is the set of integers 1, 2, 3, 4, 5, then the complement of A relative to B, or B minus A, is equal to everything that is in B but not in A, so it will be 4 and 5. So let us state something that is very useful with computing complements of sets, which is called De Morgan's laws. So let A, B, and C be sets. Then if we want to compute the complement of A intersected with B, we need to compute A complement and B complement and then find their union. And A union B complement is A complement intersected B complement. And more generally, if we are taking complement relative to some set, then A minus B intersection C is A minus B union A minus C, and A minus B union C is A minus B intersected with A minus C. All right, so these are De Morgan's laws. They are useful. We stated them. This is the end of this video. Thank you for watching it. Please put a like underneath this video, subscribe to this channel, leave comments below to support this work, and be good at math.